Hello, everyone. Welcome back. We're going to finish the our discussion on isogenies, talking about the dual isogeny of an isogeny. Just a reminder, I'm going to use this in a moment. We proved this corollary 4.11 that says that when you have a two isogenies from E1 to E2 and E1 to some other curve E3, and those are separable non-constant isogenies. If one kernel is containing the other, then there is a third isogeny, lambda, such that psi is the composition of lambda and phi. Okay, we're going to use that in a second. The key example that we are going to try to imitate with the construction of dual isogenies is this example with two elliptic curves that we already mentioned. I already showed this example that if you have an elliptic curve of this form, just notice that this is not in short Weierstrass form because of the x squared term. But in any case, if you have an elliptic curve in this format, then there is an isogeny to another elliptic curve, which also is a sort of the same shape, in such that there's this phi and another map phi-hat. They're both isogenies, and the key is that the composition of the two is not identity, so they're not inverses of each other. They're not isomorphisms, but they are. They're not they're not isomorphism, but the composition of the two is of degree 2. It's the multiplication by 2 map, the multiplication by 2 isogeny. Okay, so we're going to build something very similar, but for any isogeny. So let me tell you what that isogeny is going to be. So let phi be an isogeny. Then I want to construct something that is a dual isogeny. So it's going to be going in the other direction. Remember that there is a map phi star on divisors. So there's going to be a divisors from E2 to divisors of E1, which is given by the divisor supported on Q, maps to the ramification divisor of phi. This is in general. There is this for any a map of between curves, right? But in this case, because phi, we prove that isogenies are unramified everywhere. This divisor map is just the ramification indices are all 1. So this is the sum of P for P running over pre-images of Q. Okay. And it turns out that this map satisfies 2 different things. First, the degree of phi star of a divisor is the degree of phi times the degree of the divisor. You can see that now that if we're restricting to maps that are unramified, then that's easy to show from this, but this is true in general. This shows that the map induces a map from divisors of degree 0 to divisors of degree 0. Okay, and moreover, it also does the following: phi star of a divisor of a map F is the same that the divisor of phi star of F. Okay, so the map takes also principal divisors of E2 are going to map to principal divisors of E1. So what that tells me is that this map actually induces a map on Picard. So we're going to have a map phi star from Picard 0 of E2 to to Picard 0 of E2. Induces a map phi star from Picard 0 of E2 to Picard 0 of E1 that sends the class of P or the class of Q rather, say Q is on E2, sends it to the class of the sum of points P that are in the pre-image of Q. And this is just because the map is between this map is actually coming from an isogeny which is unramified. Okay. Moreover, also recall that we have kappa functions. We constructed these functions ki that go from ei, and they give you isomorphisms to the Picard groups. So for I1 or 2, and those send P to the class of P minus O, right? Then what I get is the following map. I have that E2 maps, I can map it to Picard for E2, and this is an isomorphism. Then I can use phi star to get to Picard of E1. And then I can use, so this was, instead of say isomorphism, let me say this is kappa 2. And then I can go via kappa 1 inverse, I can go back to E1. Okay, so I get a map from E2 to E1, okay, from here all the way to there. And this is going to be what we're going to call, this is going to be our dual isogeny. The problem is, all of these are going to be homomorphisms. However, we proved in the last video that just having a homomorphism does not imply that this map is actually a rational map. So we have to construct it somehow else so that to check that this is actually an isogeny. Okay. So let me show you what is the map actually on actual points. So what does the map do? This map, as defined, will let Q be on E2, and let P be on E1 such that phi of P is Q. Phi is non-constant, therefore surjective, so there is a P that sends that via phi goes to Q. Then let's try to trace where does our map phi-hat send Q starting from Q. So we start from Q via kappa 2. By definition of kappa 2 is going to send it to the class of Q minus O. I'm going to drop the brackets denoting class, but this is living in Picard. Okay. Then through phi star, this is being sent where Q is being sent to the pre-images, the divisor supported on pre-images of Q, and O is actually sent to a divisor supported on pre-images of O. Okay. This is the same as I can add and subtract the fact that the number of elements in phi minus 1 of Q, because we proved that for an isogeny, this is always a degree of phi. So this is the degree of phi, or which is the same also actually the size of the kernel. But that is also for the preimages of O, right? So we have the same number of preimages of O that we have preimages of Q. So I can actually write this as sum of S minus O minus sums of T minus O for S in preimages of Q and T's that are preimages of O. Okay. But then that, I know where the classes, this is classes in Picard. I know where these classes go, they go to S, and I know where those classes go, they go to T. Okay, so I know that this maps to the sum of S for S being preimages of Q minus the sum of T, where T are preimages of O. All right, but you see, if P, let me make a remark here, that if we know I've picked P such that phi of P is Q, then phi of P plus T also goes to Q, because this is phi of P plus phi of T, and that is just Q because phi of T is 0, with T being in the kernel of phi, which is the preimages of O. Okay, so it turns out then that the preimages of Q, if I know one P, then all the preimages are P plus T. So these are all of the form P plus T with T over preimages of O minus the sum of T of preimages of O, and then those T's cancel one by one, and I just have the sum of P over T preimages of O, but that is constant, and that is the size of the preimages of O times P, so, or multiplication by, and that is the degree of phi times P. Okay, so whatever this map is, it actually does this to P. So let me write that again, that we have a map that goes from E2 to Picard naught of E2 via phi star. This is via kappa 2 to Picard 0 of E1 via kappa inverse minus 1 goes to E1. And what this map does is sends P to the multiple degree of phi P. Okay, but that is actually an isogeny. That is multiplying P times a number that is multiplication by degree of phi, and that is an isogeny. Okay, all right. So so here is theorem. This is theorem 6.1 in the book. It says the following: let phi from E1 to E2 be an isogeny of degree m. Let's say degree m bigger or equal to 1, but definitely not 0, so it's non-constant. Then there is a unique isogeny such that there is, I should write that, there is an isogeny, there's a unique isogeny phi-hat from E2 to E1 such that the composition of phi-hat and phi is multiplication by m which is actually the degree of phi. Okay, and B as a group hom, we have that phi is that map, so it's K2 composed with phi star composed with kappa 1 inverse, and we've described above what it does. Okay, so let's prove this. First of all, let me take care of the uniqueness. The uniqueness is suppose that we have two such maps, phi and phi-hat, are such that, they both have that property that phi-hat composed with phi is multiplication by m, and this is also true that phi-hat prime composed with phi gives me multiplication by m. Then what that says is that then if I do phi-hat minus phi-hat prime and compose that with phi, then I'm going to get multiplication by m minus multiplication by m, which is 0. So this is constant. But since phi is non-constant, then we must have, like we saw this argument before, that if you have a composition of the two, the degree of one of the two has to be 0. So one of the two has to be 0. So taking degrees, you reach the conclusion that one of the two, either phi-hat minus phi-hat prime or phi, must be constant. Phi is non-constant, so we must have that phi hat minus phi-hat prime must be constant. And if so, we must have that they are actually the same function, because that is phi, if it's constant, it's a 0 map. And if it is a 0 map, then I can bring one to the other side to show equality. Now, if we assume that phi is separable, okay, so I'm just going to assume it here. This can be done without the separability using Frobenius, but let's assume it is separable. Then the size of the kernel is the degree of phi is m. So the kernel of phi is contained in the kernel of multiplication by m. Okay. And therefore, by proposition 411, remember, we had it here, proposition or the corollary for 11, you have two isogenies and one kernel in the other, then there is a unique isogeny that does that job. Okay, so because the kernel of phi is contained in the kernel of multiplication by m, then there is a unique isogeny phi-hat from E2 to E1 such that their composition matches the largest kernel. So that phi-hat phi is multiplication by m. So we had two isogeny multiplication by m and phi, and now there is a composition with an isogeny that gives me exactly that other isogeny multiplication by m. Okay, and so there is one isogeny that does this job, but let's see that this phi-hat by definition is the same phi-hat as defined above. Let's see, what does phi-hat do to a point Q? Well, I can, instead of Q, I can call it phi of P, but then I know that the composition of phi-hat by construction is multiplication by m, so this is just multiplication by m. which is multiplication by the degree of phi, which is what the other map does. This is exactly what kappa 1, this full composition does to Q. So by the uniqueness, then we must have that they are the same isogeny. Okay. All right. By the way, I'm not sure if I mentioned here. Yeah, here. So what would have happened if I picked another P? So maybe this is not well defined. If I pick a different P here, do I get a different map? And the answer is no. So note that if P prime is also a preimage of Q, then P and P prime differ by a point that goes to O. So P prime is P plus T with phi of T equals O, right? And therefore, what happens if I multiply by degree of phi times P? So this would, the same construction would tell me that the map sends Q to degree phi of P. So how much is degree phi of P prime? That would be degree phi of P plus T, which would be degree phi of P plus degree phi of T. But you see, this says that T is in the kernel and of phi, so it's annihilated by degree of phi, by the number degree of phi. So this is 0, so this is just degree of phi times P. So we do get that degree phi times P prime is the same as degree phi of P. So it does not depend on what choice of P I get. Okay, great. So we have an isogeny that is the dual isogeny. So that we call the dual isogeny. Page. Let phi from E1 to E2 be an isogeny. Then phi, the isogeny, the unique isogeny, phi hat that we just proved exists from E2 to E1 with the property that phi hat composed with phi is multiplication by m. Phi composed with phi hat is also multiplication by m, we'll see in a second, is the dual isogeny. It's called the dual isogeny. So let me state a theorem with properties of the dual isogeny. So here we have phi is an isogeny with degree m. Then the following properties are satisfied, that phi hat composed with phi is multiplication by m on E1, and phi composed with phi hat is multiplication by m on E2. This means that actually essentially it says that the dual of the dual, it's, or the dual of the dual is itself. Right, so the dual of phi is phi. Okay, so part B says that lambda, if you have another isogeny lambda from E2 to some curve E3, then the composition of the two, the dual of the composition is the compositions of the dual, but then you have to be a little bit careful that there's a reversal of the order. C, if I have another isogeny psi from E1 to E2, another isogeny, then the dual of a sum is the sum of the duals. Those are commutative. D, for all m, for all integers, the dual of multiplication by m is itself, and the degree of multiplication by m is m squared. Okay, and E, the degree of the dual is the same as the degree of itself, and finally the dual of the dual is itself, which I said it's related to part A. So let me just prove make a comment about part D. So about part D, this is clear for m equals 0 or m equals 1, that the dual of, well, the constant function, the dual is going to be itself, the dual of multiplication by 1, which is the identity map, is itself. So otherwise, we can do induction on m. And the induction just says the following. So I want to prove that what is the dual of n plus 1, and by part C, this is the dual of m plus the dual of 1, which is the dual of m is m, the dual of 1 is 1, and that is multiplication by m plus 1. Okay, so you can now finish the induction and say that this is true for all m. And for the degree, if d is the degree of multiplication by m, then we have that multiplication by d will be, because of the property of the dual composed with m is multiplication by the degree of m, but the dual of m is itself. So this is m composed with m, which is multiplication by m squared. And therefore, the degree of multiplication by m is m squared. And this is quite important. Right, I'm not going to prove the other properties. They're not difficult to show. I want to finish off with an application of this fact that the degree of m is m squared. Remember that the degree is the size of the kernel, so it's telling me that multiplication by m has a kernel of size m squared, so that there are m squared torsion points of order dividing m. Okay, so a corollary here is the following, that the size of the m torsion is m squared. And in fact, much more can be said, is that if the characteristic of k is 0, or in fact, if the characteristic of k and m, if the GCD of that is 1, then the m torsion is isomorphic to z mod mz cross z mod mz. So that is the abelian structure. Remember that this is the torsion over k bar. Okay. Last, if the characteristic of K is P is positive, then either you can have that the P to the A torsion is actually always just trivial for all E 1, 2, 3, etc. Or you can have that the P to the A torsion is just cyclic. Okay, so it's one or the other. Either it's 0 all the time, or is cyclic for the P to the all the time in characteristic P. Okay, so let's just prove that. So for the first part, we have just seen that the size of the M torsion is the size of the kernel of multiplication by M. By definition, the M torsion is the points that by multiplication by M give me 0, so the points of order dividing M, not points exact order M, but points of order dividing M. And that is the degree of multiplication by M, which we've just seen, it's M squared. Okay. And on the other hand, for the second part, I want to prove the actual isomorphism type. So we have that the size of the M torsion is M squared, and we also have that if D divides M, then the size of ED is D squared, and the D torsion, the points that vanish after when you multiply by D, they also vanish when you multiply by M, so you have that ED is contained in EM. And in addition, so here is a finite abelian group. So EM is a finite abelian group with the following properties. The size of EM is M squared. The size of the points that the order divides D when D divides M is D squared for any D dividing M. Then I claim that that is necessarily that has to be then EM has to be exactly Z mod MZ cross Z mod MZ. Okay, and the reason for that is that so you can compute, for example, what is a primary component. So you can do it P by P and powers of P by powers of P, and to prove that this sort of like exercise in finite abelian group theory. So in group theory. Okay. So take, for example, what is, so for example, let's write it, for example, what happens if P is prime? So we have that EP is a finite abelian group of size P squared, but also, one key property is that if P is in EM, then the order of P divides M, right? So if we have a finite abelian group of order P squared, then there are two options. It's either Z mod P cross Z mod P, or it is Z mod P squared Z. But this cannot be, because there are elements of order P squared. Okay, so it has to be this one. And you can do the same thing. Now you can build an induction, because now EP, the points of order P are inside the point of order P squared. So you can check that the point of order P squared also have to be the Z mod P squared plus Z mod P squared, because they contain this, and so on. So I'm actually going to leave that as an exercise in group theory, just verify that equality as abelian groups. Okay, and I'm not going to do the third part, although it's interesting and very useful. I'm not going to do it, because then that's when phi is it is not separable, and we are in this course. I'm avoiding the issues of separability. Okay, so that's it for isogenies, and then next time I'll talk about the Tate module. I'm skipping the section on the invariant differential, so I leave that for the students to read on their own. In the first course in one semester, I need to skip some things, so I'm going to skip that. But I'm going to be talking about the Tate module, which is one of my favorite things. It was the central object of my own thesis, and of much of my later research. So I'm very excited about that. All right, so I'll stop there. Thank you.